So in the last class, we were doing titration curves. So I explained you the titration curve of a strong acid and strong base. So few questions based on what we did last time, and then we can move to the next part, calculation based questions in which we'll calculate the pH, we'll calculate the amount and all these things. So right now we are working with titration curve. This is a strong acid, strong base. What's the meaning of equivalence point here? What's the meaning of equivalence point? Yes, the point, the titration point, when the titration ended, the point at which NaOH and HCl, both of them are 0, 0. Means HCl is completely neutralized, NaOH is both of them are 0. So what is there at the equivalence point? The salt only. And what was the meaning of endpoint? Endpoint. Endpoint is this. This is endpoint. Endpoint is when there is a change in color of the indicator, because indicator is pH sensitive. So under different pH ranges is going to show you different colors. At low pH, color is different. At high pH, color is different. So this is the endpoint. Which one is more accurate? The equivalence point or endpoint? Which one is more accurate? If you remember, endpoint you can get by adding one extra drop of NaOH. So out of these two, which point is more accurate? Which point is more accurate? The equivalence point, because this is the point at which acid and base, both of them are 0, 0. They are completely used up 0, 0. So this is more accurate. Endpoint is always with an error. One drop error. It should be one drop error. Means one drop change in color. So you're adding an indicator. All these things we discussed in the last class. And over here, who is going to determine the pH? The excess acid left. See, pH is less than 7. So during titration, in this area, excess acid is left. Over here, the excess base. Then we did the titration curve of a weak acid with strong base, this one. And here I discussed with you that this part is buffer. This part. After adding, this is the initial. This one is initial acid, whatever acid you are using. So this is initial. When the volume of NaOH added is 0, this is initial. But once you started adding NaOH, it becomes a buffer. We discussed the examples also. So today also I'm going to show you one more example. This is equivalence point. Where is the half equivalence point, children? Half equivalence point, where it is? Equivalence point you can see is at 25. Half equivalence means when half of the acid is neutralized. Yes, Vinaya is here. Anything special about half equivalence point, children? I told you few important things about the half equivalence point. Those who were not present in the morning class, don't worry. This titration curve we are going to make with the help of one question. So just pay attention what I'm saying. Try to understand simple things. Equivalence point, when the acid and bases, both of them are 0. Both of them are 0. But can you see the equivalence point has a pH of 8.72? Because here, this is the one who is going to determine the pH. And CH3COO minus is a strong conjugate base. So the salt is basic. This salt is basic. That's why the pH is basic. Half equivalence point is the point when the concentration of the acid and the concentration of this conjugate base are equal, because half of the acid is converted into its conjugate base. Half of the acid is converted into conjugate base. Acid is still there. Half of it is reacted, half has reacted, half is still left. So these are equal. This is a weak acid. This is its conjugate base. So what does it mean? It means it's the buffer, best buffer. At the half equivalence point, pH equals to pKa. Can you memorize these things right now? We'll understand this also. I gave you example in the last class also. But today also we are going to do one titration to understand this. Are we getting this, children? And here the pH over here is determined by axis of the base. Axis of the base. After the half equivalence point, you are adding extra amount of the base. See, this area is axis of base. That will come here. pH jumps very strongly around 11 and 12 because NaOH is very strong base. So children, can you write down about the half equivalence point here? In the titration of a weak acid with strong base, you are going to get a basic salt. So before the equivalence point, before you reach the equivalence point, you are getting a buffer area because there is weak acid with the salt buffer. So can you give me all important points about the half equivalence point? What will be the half equivalence point? Best buffer. It's a very important question. Half equivalence point is best buffer. And what is a best buffer? When pH equals to pKa. That's the best buffer. Henderson equation. Remember Henderson equation, pH equals to pKa plus log concentration of A minus over HA. Best buffer, pH equals to pKa. The concentration of acid is equal to the concentration of its conjugate base. Half of the acid is neutralized. So please write down these points. So in this titration curve, where is the best buffer? Here at the half equivalence. Best buffer means minimum change in the pH. You can see that it's nearly flat in this area. The pH here, Sarayu is there? Yeah, Sarayu, you can see that? It's nearly flat. Saranya, nearly flat. Means pH is hardly changing. So it is the best buffer. So please write down these important points. I'll keep asking this question again and again. And if you in your mind, if you say, why is it like this, pH equals to pK? So as I said, we are going to do one question where we are going to make this titration curve and everything will be clear there. Because I did in the previous class also, but we'll do it again. Ready for next graph? Strong acid with weak base. Let's say the strong acid is HCl and the weak base is ammonia. I'm doing titration of ammonia with strong acid. Look at this pH curve. What are you adding? Check. Are you adding acid or are you adding base? You're adding acid. So what is there in the burette? Because what we are adding is, should be in the burette. And what is there in the conical flask? These are experimental questions. So if this data is given to you, can you identify what is there in the burette and what is there in the conical flask? Can you identify what's there in the burette? Yes, HCl, because HCl you're adding. So you're opening this knob and HCl is added. And what is there in the conical flask? Ammonia. Now answer the next question. All of you, please try to answer. Where is the pH meter? We are using a pH meter to measure the pH. Where is the pH meter? Is it in the ammonia or is it in the burette? Where is the pH meter? Where should I place the pH meter to observe this pH? It is in the ammonia here. Yes, because only the pH of this conical flask is changing. Here is the pH meter, the instrument which we are using to measure the pH. It should be dipped in ammonia. Very good, Saranya. Why should it should be dipped in the ammonia? Because reaction is taking place here, not here. HCl is not undergoing any change. Only volume is undergoing a change. You are mixing them here in the conical flask. So everything is happening here. Where is the indicator? If I'm using an indicator, where is the indicator? Indicator is also here. Indicator is also in the conical flask. How much indicator we should add? Only a drop, few drops. Few drops, 1 or 2 drops. That's it. Indicators are very sensitive. Indicators are very sensitive to pH. So once they are in the ammonia, pH is high. You can see ammonia is a base. pH is high. Indicator has a different color. But after the titration, at the equivalence point and above, you can see there is a big change in the pH, big drop. This is called as endpoint. Your indicator will show you a drastic change in the color at this particular point by adding one extra drop of HCl. It will show you change in color because of the, yes, who is going to answer? The indicator is showing us change in color because of the, yes, anyone? Because of the change in pH, drastic change in pH, big change, like this big drop. This is going to drop from pH this from 7.88. All of a sudden the pH has become 2.70. See, this is a big drop. And due to this big drop in pH, there is a change in color. Is it okay? You're understanding this? Yeah, please say yes or no. Vinaya, is it clear that why the indicators are changing color? So indicators are changing color because of the, okay. Now this is the equivalence point. And what happens at the equivalence point? Similar question what I was asking earlier. What happens at the equivalence point? Do I have any HCl? What's the amount of HCl at this point? Zero. What's the amount of ammonia at this point? Zero. So what is there at this point? Ammonium chloride. What kind of salt is this? Acidic. Because Ammonium is conjugate acid of this weak base. Ammonium is stronger conjugate acid. Stronger conjugate acid. Type of salts which we have already done. So that is the one who is going to control the pH. So it will come into water, will break down into hydronium, and pH will be less than 7. Check. pH at the equivalence point is less than 7. pH is less than 7. It means at the equivalence point you have acidic salt. Dhruv, is it confusing? Okay, good. Okay, so here is the equivalence point. Where is the half equivalence point? Identify half equivalence point. Yes, here. And can you see this is again buffer area. So what are the properties of this half equivalence point, children? Can you write down here? A half equivalence point is best buffer. Yes, Vinaya, good. pH equals to pK. And concentration of the acid is equal to the concentration of this conjugate. And like here right now I have a base. So I can say the concentration of the base is equal to the concentration of his conjugate acid. And best buffer. Don't forget this word. It's the best buffer area. You can see minimum change in pH. Minimum. The line is nearly flat. So that's about your titration of a strong acid and weak base. So whenever you are doing titration using a weak acid with a strong base or using a weak base with a strong acid, buffer is formed. Buffer is formed. Before you write down this, before the equivalence point, before you reach the equivalence point, buffer is formed. So please write down this. I'm going to clear it. Can we do this question now? Consider this titration curve of a weak acid with a strong base. Here is the base. So indicate the equivalence point. Yeah, where? Where is the equivalence point? Okay, I'm marking the points here. A, B, C, D. So which point indicates the equivalence point? Yes, the C point. When you see the sudden jump in the pH, this sudden jump, it means acid is neutralized and you are getting the base. Okay, I'm highlighting two lines. One is this one, up to here. Other one is this. Which line, which highlighted, you can tell me in terms of color, which highlighted line is indicating excess of acid? Which line? The excess of acid is there, Sanjana, acid. If it is acid, then pH should be more than 7 or less than 7. Excess of acid. Which line? Yes, Vinaya? Which line is telling us excess of acid? See, at the equivalence point, you know, equivalence point is the one where the acid is 0, the base is 0, this point. Below equivalence point, this yellow one. Yes, this is excess of acid, excess of weak acid. And where is excess of base? Sanjana, you have understood your error? Yes, this is excess of base, this one. Excess of base. Okay. Where is the half equivalence point? Indicate the half equivalence point. In this titration curve, indicate the half equivalence point. Yeah, it is B, this one. That is the reason for maximum buffering, agreed? You remember this is the best buffer area? Maximum buffering, you can see the line is nearly straight. No change in pH. Best buffer area. Answer this, C. Where can you see this point? Are you answering this, Sanjana? Where can we see this point? Yes, same. Half equivalence point. I told you all the properties of half equivalence point, which is very important question in AP, in the multiple choice questions. Half equivalence point is best buffer. Half equivalence point has pH equals to pKa. Half equivalence point when half of the acid is neutralized. Okay, D, this question. In the titration curve, where the pH is determined by only acid, only acid. This also I told you in the previous titration curves. Only acid, no one else. Initial, when the volume of this base added is 0. Here the pH is determined by only acid, no one else. Because nothing added. So this point is due to only acid. pH depends only on A minus. A minus is the conjugate base. So that is the point when HA should be 0 and the base, whatever base you are using, should be 0. So where? Very good, Vinaya. Very good. C. C is the point when it is going to be your only the base is going to determine the pH. Lasya, Sanjana, is it okay? C point. Okay. This one. Yes, Dhruv. Shrihan, you're not answering today? Change your name, please. You're not answering, Shrihan? Okay. What about the answer of this? pH depends on the amount of excess base. Amount of excess base. It's written on the graph. Where? Which point? Please answer. Dhruv, answer it. Which point on the titration curve indicates that you can determine the pH because of the excess of base? Vinaya, it's a very simple question. It's written on the top. Yeah, so why you people are taking so much time? Yes, D, Sarai, you good. Okay, let's do this graph again. I'm marking the point. Okay, how to determine pH at this point? How to determine the pH? Pick up the option from here. At this point, how to determine the pH? Only, yes, which option is good? Yes, only acid. D option, this one. Only acid. What is this point? Pick up the option. What is this point? Yes, Dhruv. Yes, C and B. This is the point of maximum buffering. What is the other name of this point? Other name. The other name of this point during titration. No, Vinaya, no, no, no. It's not equivalence. It's not the end of the half equivalence. Yes. Halfway. Yes, Ashita. And what is this point? This one. This is the equivalence point. Complete neutralization. This one. And how to determine the pH at this point? How to determine the pH at this point? Which option? This one. Access base. You will use the base to determine the pH. Is it okay? Now, where can I see the change in color of the indicator? Can you mark the area? Like if I put like this A, B, let's say this is C, let's say this is D, let's say this is E. So which area will show you? Which part of the titration curve will show you the change in color of the indicator? This one, children, this one. No, this complete. It has a different color in this area. At the C point, different color. And at the E point, different color. Because of big change in pH. Big change in pH. And indicator changes its color. Change in pH. Okay, when I'm going to teach you indicators in the last, only 1 or 2 slides are there. Then I'm going to tell you that how these indicators, they change their color. What is the reason that they are changing their colors? Okay, ready for next question? This time we are going to make a titration curve of a weak base with strong acid. So let's make it. Here is the pH. Here is the volume of strong acid. So I will start from, because strong acid is here, volume is 0 here. So when the volume of acid is 0, pH is determined by weak base. So let's start somewhere around 11. Base is high pH, more than 7. And the titration curve will go like this. Okay, I have to make it again. Like this. Now start answering questions. What type of salt is this? Acidic, basic, or neutral? What type of salt is this? Yes, it is acidic. So where is the equivalence point here? A part. Where is the equivalence point? We are doing this one. Where is the equivalence point? C. This equivalence point is due to this salt, BH plus, because at this point only BH plus is going to determine the pH, because it is a strong conjugate acid of this weak base, right? So what will be the pH at this point? More than 7 or less than 7? The pH at this point, more than 7, less than 7. Yes, less than 7 because it's acidic salt. Okay, where is the reason with maximum buffering? Maximum buffering means best buffer. Where is it? Yes, B point. Very good, Siri. Now, what is the other name for this B point? Other name. Half equivalence point. What's the meaning of half equivalence point? That half of the acid is neutralized and half of the base, sorry, we are doing base here. Half of the base is neutralized and half of the base is still left. Only half of the base is neutralized, means reacted. And Sanjana is right. This is also half equivalence point, this one. So both of them are best buffering area and half equivalence point where half of the base is neutralized. D part. Very good, Vinaya. A is the point where you have only the base. See, acid is 0. So A. E part. pH depends only on BH plus. Lasya, you're there? Yeah. You're not answering, Lasya. Are you confused? We are doing E part. So this should be C. The equivalence point, it should be C. What about this one? pH depends on excess of the strong acid. Yes, here. This is excess of the strong acid. After the reaction, after the equivalence point, you are still adding acid into it. Where can I see the change in pH? If I mark these points, I'm giving you 2 more points here. Let's say this is E, let's say this is F. So where can I see the drastic change in pH? From E to F. So where can I see the change in color of the indicator? From E to F. Indicators, they change their color due to drastic changes in the pH. We are good with this? Okay. Now, these are about titration curves. Now we are going to make our own titration curve. We'll make a titration curve. We are doing a titration. Read the question. In the examination, they will not ask you such lengthy question. I'm doing this one. They can give you only one volume. Like here we are using so many volume. They can give you any one volume, this one or this one. But we'll do with all the parts. That will give us a good practice. And we'll identify everything. And we'll make a pH curve. Ready, all of you? pH curve. We are making a pH curve here. Fine. Let's start. So there is perchloric acid titrated with KOH. So what is there in the burette? Read the question. Which volume is changing? So what is there in the burette? What's there in the burette? This is the burette. So what will be there? Yes, KOH. KOH. Burette has a stand also. It cannot be hanging in the air. It has to be with a stand. And there is a conical flask. Here. Oh. So what's there in the conical flask? Conical flask has HClO4 here. How much volume of HClO4 in the conical flask? It's given in the question. 40 ml. It's given in the question, right? And where should be the pH meter? pH meter. Where should I place my pH meter? In the conical flask. You will place your pH meter here in the conical flask. Ashita, we are doing titration. Read this question. Ashita, read the question. We are doing titration and we are going to do calculations. pH meter is the conical. Where is the indicator? Where should I place the indicator? In the conical flask. Yes, because the reaction is carried out. Where is the reaction taking place? In the conical flask. So changes are happening in the conical flask, not in the burette. Okay, so you place your indicator in the conical flask. You place your pH meter in the conical flask. And now let's start. Very first part, A. You have not started the titration. So first let's write down the reaction. HClO4 going to react with KOH to give KClO4 plus H2O. It's a double displacement reaction. H plus is going to OH minus, ClO4 minus is going to K plus, like this. A salt is formed and water is also one of the product because you are taking KOH. Okay, this is the equation. Now let's do A part. We are doing A part, children. In the A part, this is the reaction. We are going to write down initial and final. So how much HClO4 is there? Can you work in millimoles? How many millimoles of HClO4? I'm working in millimoles because I'm going to add the volumes. Though I'm not adding any volume in the A part. So in the A part, KOH is 0. It's totally 0. So the pH will be determined by the concentration of H plus, which you are getting only from HClO4. It's a strong acid which is going to dissociate completely 100%. The concentration of the strong acid is given to you as 0.200 molar. Reaction has not started yet. And this will give you how many millimoles, how many molarity of H plus? I need molarity now. How much molarity of H plus you will get? The same molarity. Yes, because it's 100% dissociated. So what's the pH? Negative log of 0.200. How much is that? How much is that? 0.699. Very good. Only Vinay is doing calculations. All of you can do it. This is nothing new. So where should I put this mark in the titration curve? Let's say this is 7. So where? Here. When the volume of KOH added is 0. This is the A point when you have not yet started titration. The pH is determined by the pure acid. I was showing you this point in the earlier titration curves. So who is going to determine the pH at this A point? Only HClO4 because nothing else is there. Is this point clear? The first point? So the pH for the first one is 0.699, which I marked here. Now let's do the B part. B. Now I'm adding volumes. So I will start working with millimoles. So can you work out the millimoles of your HClO4? Millimoles? Yes. Sarayu, what's the equation for millimoles? Molarity times volume in milliliter. This one, right? So how many millimoles, Sarayu? Can you calculate? Calculate the millimoles of the, I think Vinaya calculated earlier. She told me. You just multiply these two. Multiply. How many? 8.00. Three significant figures, right? Is it correct? 8.00 millimoles. In the B part, you are adding KOH. Can you work out the millimoles of KOH? Millimoles of KOH. This is the molarity. This is the volume. So how many? Mhm. Millimoles of KOH. Use this equation to get the millimoles of KOH. Yes. No, 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 no. What you did, Siri? Which two factors you multiplied? What's the volume of KOH, children? 10. And what's the molarity of KOH? 0.1. Multiply these two. Is 1.00. Is it okay? Yeah, good. Initially, no product, right? Reaction has not started yet. Now reaction has started. After the reaction is completed, how much HClO4 there? How much KOH? Who is the limiting reactant? Yes, how much HClO4 here? How much KOH? How much KClO4? 7. KOH? KOH is 0. Who is the limiting reactant? KOH. Is there any base present? No. KClO4 is 1, right? KClO4 is 1. Now check final situation. Water, of course, is there, but we are not interested. There's plenty of water. Now look at the final situation. Who is stronger here? Who is going to control the pH in the B part? Who will control the pH? Who is stronger? We are doing B part. You have this and you have this and you have water. Who is stronger? Who is more stronger, acid or base here? It's very simple question. Whoever is stronger will control the pH, will determine the pH. You will use that amount. Yes, Vinaya, yes. This acid is stronger. This acid is stronger. Stronger than this KClO4. This base is stronger, but base is 0. Base is also very strong, but it's 0. So acid is going to determine the pH. But for that, I need to know the concentration of HClO4. Concentration of HClO4 is millimoles of HClO4 divided by volume in ml. Do I have the millimoles? Yes, 7.00, this one. And how much is the total volume? V total? You are mixing volume. That's why we are working with millimoles. V total is 40.0 plus 10.0 is 50.0 ml. Volume changes. This added in this. These two are added. So it is 50.0. That's the concentration of HClO4. And what is the concentration of H plus? It's a very strong acid, 100% dissociated. Don't you think H plus will also be the same? Same concentration. This is equal to concentration of H plus. What is the reason? It's a strong acid. It's 100% dissociated. It's fully dissociated. So the concentration will remain the same of H plus. How much is it? And get the pH then. This concentration I'm getting as 0.140 molar. So get the pH now for the B point. pH is negative log of H plus, right? How much is that? Is 0.854. Yes, very good. Now at the B point, the pH is determined by excess of the acid. We have not reached the end of the titration. We are still doing titration. Acid is not completely neutralized. Acid is still there. Can see acid and pH. Now this one, the first one was 0.699. This one is 0.854. So move slightly up, slightly up. This is for 10 ml. Let's say this is 10 ml. Go like this, slightly up. This is your B point. Here you determine the pH by excess of base. Oh, sorry, excess of acid. Acid is not neutralized completely. Excess of acid. pH is less than 1, less than 7. And is also less than 1 because it's very strong acid. So A and B are done. Exactly in the same way, you are going to do the C part. Same method. Everything now repeating. So we are on the C part. This one. Only thing you have to make the table again. This table. Let's make it again. Reaction is the same. So how many millimoles of HClO4? No change. Same. Same millimoles of HClO4. So what is changing? Amount of KOH. So how many millimoles of KOH you have added? How many millimoles of KOH we have added? Srayu, can you do the calculation? And if you are confused with millimoles, then you can work with moles also. That's not a problem. I prefer to work with millimoles because numbers are slightly handy. If I convert everything by to mole, then I have to divide everything by 1000. Extra calculation. Yes, 4 millimoles. Very good. Initially, before the reaction, these are 0, 0. Water, not interested. Okay, F. Final. Yes, can you complete it now? Complete the final. Check who is left, who is used up completely. Means which one is the limiting reactant and which one is excess and how much of that is left. Yes. Can you see, children, what Shri is showing us? This is okay. Yeah, very good. What is it, children? Don't you think that half of the acid is neutralized? Can I say this point as half equivalence point? You are learning so many things about half equivalence point, but this is a strong acid and strong base titration, so you're not getting a buffer here. So don't expect a buffer here because both of them are strong. Salt is neutral. Strong acids, strong bases, they don't give you buffers. For the buffer, the condition is the presence of a weak acid with its conjugate or the presence of a weak base with its conjugate. But this is half equivalence. You can identify half equivalence, children. So get the pH. Who is going to determine the pH? Answer this. I want to determine the pH of this final solution. Who will determine the pH? Yes, again HClO4, but the concentration has changed because you are mixing volume. The millimoles are also changing. So what's the concentration? 4.00 millimoles, the amount which you can see here, divided by total volume. What's the total volume, children? All of you, please type the total volume for the C part. Total volume for the C part. Yes, very good, Vinaya. Good thinking. So don't you think that this is a strong acid, so the concentration of H plus will be the same because it is 100% dissociated? 100%. So it's fully dissociated. So I'm taking the same concentration. So what's the pH? Negative log of this concentration. How much is that? 4 divided by 80. Negative log of 0.05. And the pH is 1.301. Yes, very good, Sanjana. Perfect. So the graph will go slightly more up. This is half equivalence point has a pH of 1.301. So from 0.8 it has gone to 1.3. This is 40 ml. So graph will go more up like that. It's not a buffer. pH is changing, right? Big changes are happening. Now let's go to the D point. Ready for the D? Same procedure, everything same. So help me in completing the table for the D point, and then we'll calculate the pH. Dhruv, we are doing D. So how many millimoles of HClO4? Because you added this volume into this. So how many millimoles of HClO4? Calculate millimoles the way we were doing earlier. Mhm. Millimoles of HClO4. Dhruv, Sarayu. For the D part, how many millimoles of HClO4? Yes, Vinaya, thank you very much. Every time Vinaya is telling me about the millimoles, rest of you are confused about it, how to calculate? Every time Vinaya is answering. Shrihan, is it okay? How to calculate this? So why you are not answering? See, when you don't answer, it means you are slowing down the session. If you know the answer, why don't you answer it? Is it going to take so much time? You are slowing down the session by not answering the questions. Dhruv, I want your full attention here. KOH. Can you tell me how many millimoles of KOH you have added? Millimoles of KOH. You are adding 80 ml of 0.100 molar. So how many millimoles of KOH? Waiting for the answer. It's very simple question I'm asking. Equation is written here. Molarity times volume. Yes, Sarayu. How many millimoles of KOH we have added at the D point? Yes, 8. 8. Yes. Okay, initially this is 0. Finally, what happens to this and this? Complete the final table the way you were doing earlier. Give me everything. Water, we are not in need right now. Water is there. Yeah. So what is this point called as? Both acid and base are 0. What is this point? This is your equivalence point. Equivalence. Who is stronger here? Water is also there at this point. Who is stronger? Now pH will be determined by these two because rest all are 0. But out of these two, which one is stronger? Water, yes, it's a neutral salt. Strong acid, strong base, neutral salt. So what's the pH of water? We need not to calculate. pH is due to water. So pH is 7. So from this 1.301, from this, you are going to have a big jump to 7. You're here. Equivalence point here. And what's the volume? Okay, I think I have to take care of the volume also. Volume is 80, like this. So you can go and you're going to show a jump at 80. And this is the equivalence point. Let's go to the E part. E. Same thing, same procedure. All eyes here, please. If you're doing something else, stop doing. It's a very interesting question we are doing. It can be in multiple parts. It can be only one part. They may give you only one part of the titration and they will ask you to calculate the pH. So first write the equation, reaction, then how many initial millimoles of HClO4? Keep answering very fast. You already know. There is no change in this amount. How many? How many initial millimoles of HClO? HClO4. Why? Why 20? Why 10? What's the molarity of HClO4? What's the volume? Is this the volume of HClO4, children? What are you doing? Yes, Sanjana. Yes. Dhruv, you have understood your error? Still the 8. This is the volume of KOH. So how many millimoles of KOH? Yes, Ashita. How many millimoles of KOH? Yeah, 10. Initially this is 0, 0. Complete the table. Don't wait for me. Now you know how to do. Complete the table. Finally. 0. KOH. How much KOH left? Dhruv. KClO4. Yes. Who will determine the pH now? Check who is stronger. Water is also there. So we have KOH, we have KClO4, we have water in this conical flask. So who will determine? Yes, KOH. But I need the concentration of KOH because KOH is a strong base. It is 100% dissociated. So it will give me the concentration of OH minus also. And that is millimoles divided by volume in milliliter. How many millimoles of KOH we have? 8, right? And how much is the total volume? Total volume in the conical flask, in this flask, total volume. Yes, very good. Get the concentration of OH minus, but OH minus will give you POH, negative log of OH minus. So that's going to give you POH. And POH is yeah, what's the pOH? Anyone doing calculations? It is the negative log of OH minus concentration. I have already given you the formula for the OH minus. So yes, Ashita, I'm also getting the same. Very good. But the question is asking pH. So what's the pH then? We are making pH curve. This is pH. pH will be 14 minus, yes, through POH. How much is that? 12.76. So the pH will be, so there is a jump. You can see there is a jump. And then the graph will go to some height like 12 and like this. So there is no space. So I'm making a curve like this. Like that. Okay. So can you see that finally in the titration, the pH is controlled by excess of base. At the equivalence point, pH is controlled by water. It's a strong acid, strong base. Before that, pH is controlled by the acid. This point, pH is controlled by the acid, excess of acid left. But the concentration is changing. So every time I have to calculate the new concentration of the acid because volumes are changing, millimoles are changing. So get the new concentration of acid, get the H plus ions concentration from there and calculate pH. So just showing you the graph here again, not according to the scale, just showing you the shape of the graph like this. This is excess of the base, excess. This is excess of the acid. This is equivalence point. This one is initial pH of the pure acid when volume of the base added is 0. You're understanding all these? This is a simple titration of a strong acid and strong base. Now we have to work out the titration of a weak acid with weak base. That is the last question on titration. Weak acid with strong base, sorry. Last question on titration. I want all of you to participate and keep guiding me. This is slightly complicated. It's not complicated, but here you're dealing with weak acid. So you will get a buffer. So you'll be using Henderson equation. And then you are getting a strong conjugate base at the equivalence point. Then you are making Rice table for that to know the pH. So things are slightly different here. So shall we start? What should I do first? Very first thing that you write down the reaction. KOH is there. You can see this formula will be given to you. It is HC2H3O2. And then it's undergoing titration. You're adding them. It's a weak acid, but there is a strong base, so actually no equilibrium because of the presence of this strong base. No equilibrium. It's going in the forward direction. K plus will combine with this acetate. So you're getting this salt. This is the salt. And what else? Water. Okay, now let's do the A part. So we are going to make a titration curve. This time I'm going to make it here. This is pH. And this is volume of what? KOH. You're adding volume of KOH. Starting volume of KOH is 0. Will go up to 250. So now explain the setup. What is there in the burette? What is there in the burette? Hmm? QH, yes. And what is there in the conical flask? In this conical flask, what is there? Acetic acid, yes. If you don't remember the formula in the exam, just take it as HA. More easier, right? So if something is not striking you, you don't have time, then use this generic acid kind of, because generally they will give you monoprotic. They will not give you diprotic or triprotic. So take HA, right? Okay, now you're doing titration. You're adding KOH. Where is the indicator? Here, indicator. How many drops? Few drops. Few drops of the indicator here. And where is the pH meter? Few drops. Where is the pH meter? In the conical flask. Sanjana, very fast. Very good. Here is the pH meter. We all have pH meters, pH probe. We call them as pH probe. We have pH probe in the labs. If you want, your teacher can show you. Okay. So you dip the pH probe in the any solution, it will show you the pH of that solution. So generally children are checking the pH of drinking water, pH of tap water, like this. pH of different pH of milk. So you put your probe in the milk, it will show you the pH of the milk. Okay. So this is the reaction. Let's start with the A part. A part. Who is going to determine the pH in the A part? Because KOH is 0. So who will determine the pH? Only the acid. See, KOH is 0 in the A part is 0. So who will determine the pH? Only the acid. So there is no change in concentration because you didn't mix up any volumes. So you can start with your acid. What kind of acid is this? Is it a strong acid or weak acid? This acid is strong or weak? Children, are you listening? Vinaya, thank you. What about rest of you? Can you give me the reason why it is weak acid? Why you're saying it's weak acid? Because it's carbon containing. Yes, it has carbon, right? So if it is a weak acid, then don't you think that to determine the pH of a weak acid, I will set up an equilibrium because it's not 100% dissociated. So an equilibrium is needed now. I'll make the rice stable. Reaction, initial concentration, change, equilibrium. Remember, rice tables are always in terms of molarity. They are always in terms of molarity. They are never in terms of moles or millimoles, okay? Molarity. And that molarity we know is given 0.200. This one. Complete the rice table. You already know how to do it. X is the change, that much amount dissociated, minus X, X, X. Now, look at the Ka value. Ka is the equilibrium constant for a dissociation of this acid, which is the concentration of the product of the product concentration divided by concentration of, right? Plug in these values. Can I do approximation? In fact, I told you in the last class also, if it is 10 raised to, yes, Shriyan, very good. It is 10 raised to power minus 5 or less. Go for approximation. You can check later on the degree of dissociation, x squared. So I'm doing approximation, children. You remember the approximation, how to do? That you are going to take this value, this x negligible. So when you subtract or add, then it is just 0.200. So it is 0.200, which is equal to 1.8 times 10 raised to power minus 5. Get the value of x from here. And that value of x is the concentration of H plus. See here in the rice table. X is the equilibrium concentration of H plus. And that is 1.8 times 10 raised to power minus 5 times 0.200 square root. How much is this? So this is how to determine the pH of weak acid. This topic we have already done. For weak acids, weak bases, we have to make the rice table because they have equilibriums. Anyone doing? I'm getting 1.90 times 10 raised to power minus 3 molar. Get the pH. So you take the negative log of this answer. I'm getting 2.72. We are taking 2 sig fig or 3? Right now we are working with 3. So where is this point in this pH curve? Where should I put it? For the A point, when the volume of KOH is 0, put it here somewhere. Can you see the pH is slightly higher than the strong acid pH? Here is it. So this pH is 2.723. This is the starting before you start the titration, initial. This is the point when the pH is controlled by the acid only, A point. The pH is controlled by this weak acid. Children, this is clear? This we have already done, how to determine the pH of weak acids. And because A point, at the A point, titration has not started, we have not added any KOH. So it means it's only pure acid. So get the pH by making this rice table. K is given to you. Now we are going on the B point. 50 ml. Let's say this is 50. Okay, tell me how much now because you are adding volumes. See at the B point, 50 ml and 100 ml are mixed together. So at the B point, what's the total volume? Total. What is it? What's the total volume? Again, only Vinaya. What about rest of you? Yes. Saranya, you're there? Yes, Lasya. Good. Sanjana, Siri, keep answering. Keep helping me in few things. It will keep you engaged with what I'm speaking. Otherwise, you will start drifting away. Okay, now work out the millimoles. Because now I'm going to work with millimoles. Because I have added two volumes. Concentrations will change. So this 50 should be multiplied by this 0.100 KOH. So how many millimoles of KOH you have added? Isn't it 5.00? How many millimoles of the acid? Correct? Finally, complete the final table. Any one of you, please help me with the final. Check who is the limiting reactant, who is in excess. Limiting reactant will become 0. Proof? That's what I'm asking that. When I'm asking the millimoles, no one is answering. So I was thinking that you don't know how to calculate it then. Can you see the molarity of acetic acid? And millimoles, I told you, is molarity times volume. So what's the molarity of the acid? 0.200. What's the volume? 100.0. You have to read the question carefully. Dhruv? Oh, is it? Children, is this part visible to all of you? Oh, you have to take care of your screen. Dhruv. I also have the problem with one of my screen, but I corrected it yesterday. There is something, somebody corrected it for me, but I don't know how. But I think there's some resolution, something like that, that you have to adjust. Okay, can you give me the final now, children? Final. Yeah, 0, 15, and 5, and water. Who will determine the pH now? So first, before you answer who will determine the pH, do you think it's a buffer? Do you have a weak acid? Yes. Do you have its conjugate? This is its conjugate. Do we have? Yes. It's a buffer, children. Don't make any rice table. Use this equation. pH equals to pKa plus log concentration of the A minus, which is your C2H3O2 minus. You can write that if you want. C2H3O2 minus over concentration of the acid. To know the concentration, I'll take these millimoles. If I want to convert this into concentration, I'll take the millimoles and divide by 150. So I'll take this as 5 divided by 150. And for this also, I'll take 15 divided by 150 because volume is same for both of them. Don't you think that volume cancelled? So rather than taking the concentration, you can take the ratio of the millimoles because their volume is same. It's a ratio. So volumes cancelled out. So you need not to calculate the concentrations. You can simply convert your millimoles. Take the ratio of the millimoles. Don't get the concentration. Now this has become very simple. You know pKa? So what is pKa? Negative log of Ka. Log. I'm not calculating concentration because the volume is same. So I'll take the ratio of the millimoles. That is 5 over 15. Negative log of Ka is how much? K is given. Children here, Ka. Dhruv, you can see it? Is 4.74. And this value will be, okay, Vinaya is asking why I'm not using the concentration. So Vinaya, can you tell me what is the concentration equation? What is the concentration of C2H3O2 minus? Millimoles divided by volume. How many millimoles? 5. What's the volume? 150. What about this one? 15 divided by 150. Same volume, 150. They are together in the same solution. You have mixed them. Now the final solution is 150. So these 15 millimoles are in 150. This 5 is in 150. So if I take the ratio, don't you think 150, 150 cancelled? So that's why I said don't convert. If you put it here like this, 5 divided by 150, check here, children. I'm placing the volume here. 5 divided by 150, 15 divided by 150, cancelled. So we can take 5 over 15 straight away to save time. And this answer will be, this value is less than 1. So pH will be less than pKa. We did this question, right? pH will be less than pKa. Okay. Sanjana is giving me this value as minus. See, it's the minus value because the number is less than 1. So is the final answer 4.27? 4.27. So the pH here is 4.27. Can you do the C part now? We are working with C part. C. I have to erase few things. I have to erase this setup that we have understood. And this also we have understood that in Henderson equation, during titration, I can take the ratio of the millimoles. Complete the table for the C part. Complete this table. KOH 100 times 0.1. So KOH is 10.0. Acetic acid is still same, 20. This is initially 0, right? Final KOH is 0. Acetic acid is 10. This one is 10. Is it still a buffer? Is this still a buffer? Yes. Weak acid and its conjugate. What else is this? It's a very special point. They are equal. But a very special point. What is it called as? Can I say this is the half equivalence point? I should get pH equal to pKa. It's still a buffer. So I'm still going to use my Henderson equation. pH equals to pKa plus log the concentration. Now they are same, 10 over 10. So what is pH? pK is still the same. It's the same acid. So the pH is 4.74. So here the pH is 4.74. You added 50 ml of KOH. There is still acid, but the concentration has gone down drastically. But still the pH is not changing. Not much change. It's not a big change, right? So when I put these points here, this is, let's say, this is pH 4.27 B, and then you can see this is 100 ml, right? And it is half equivalence point, and you can see that pH equals to pKa because log 1 is 0. Half equivalence point. We have reached the half equivalence point, children. Now let's do the D part. Ready for D? KOH. Give me initial, all of you. I'm not writing anything. I'll wait for your answer. Give me initial for the D part. How many millimoles? We are still working with millimoles because we are adding volumes. Give me initial for the D part. Yes, Dhruv. How many millimoles of KOH? Millimoles. Molarity times volume in milliliter. 15. Okay. And how many millimoles of acetic acid? 20. 0. Final. Make the final. Siri, you are not answering. I cannot see your name here. Ashita, Lasya, Lasya, where are you? I have to scroll down the names to see who is answering and who is not answering. Saranya, you are not answering. Yeah, now you are answering. Good. So final is 0, 5, and 15. Is this still a buffer? Can I say still a buffer? Because there is a weak acid with this conjugate. Still a buffer, right? Okay, good. Use Henderson. pH equals to pKa log. Now how much is the conjugate base? 15. And the acid? 5. pKa is still the same, 4.74 plus. Now this value is greater than 1. You'll get a positive answer. So pH will be more than pKa. These things we did earlier. So how much is the pH? 5.217. Because your log of 15 over 5 is a positive answer. It is 0.477. So when you add them, you get this answer, nearly. Okay, I'm audible? Yeah. Yes, yes. Okay, sorry. In between. Okay. There is some problem with my system. By the time we have done the D, can you try E part? Oh, it's working now. E part. So let's make the table for the E. And in the D part, the pH is still less than 7. It's 5.2. You can see this is the best buffer area, minimum change in pH, half equivalence point. Now we are working with E. Complete the table for the E part, children. Very good, Vinaya. 1 is to 20 and then 0. Finally, oh, is it 20? Not 1, 20. Finally, both of them are 0. So who will control the pH now? The conjugate base, because water is weaker here. The conjugate base is stronger. So in the E part, who is controlling the pH? The controller of the pH is C2H3O2 minus. It's the conjugate base of the weak acid. But it's also weak. It's not very strong. It's also weak. So I need a rise table again. And can I say this is the equivalence point? This is the equivalence point. And at the equivalence point, this is the base who is going to control the pH. It's stronger than water. So I'm going to write down the equation of the base with water to make the rise table. It's a base. It's an acid. Base will force water to behave like an acid. So you're getting HC2H3O2. The base is accepting a proton and water is donating a proton, so OH minus. Aim is to know this OH minus. You can see my writing up to end here. Is it visible? Okay. But this is rise table now. I cannot work with millimoles. Rise tables are always in terms of concentrations. And if you are dealing with gases, pressures, never in terms of millimoles. But I have the millimoles here. So can I get the concentration of acetates? 20 millimoles divided by total volume. What's the total volume, children? Total volume is 300, right? 300 ml. Can you work out the concentration? So I'm working out the concentration of the conjugate base because I have to make a rise table to know the pH. So that is the reason we need concentration. Rise tables are always in terms of concentrations, like this. Is it okay? Now initial, this is initial. So I can take these two 0, 0. Change, so rise table change. Let's say X amount has dissociated. Then this is plus X. This is plus X. Equilibrium 0.0667 minus X. X, X. But I need Kb. It's a base dissociation. You're getting OH minus. It's a base dissociation. So I need Kb. Kb is the concentration of H C2H3O2 times concentration of OH minus over concentration of C2H3O2 minus, right? This is Kb, but Kb is not given. What is given? Ka. So I need to calculate Kb from Ka. How much is that? Kb will be Kw over Ka. You remember this equation, children? When you plug in the values, Kw, 1.0 times 10 raised to a minus 14. Ka, 1.8 times 10 raised to a minus 5. So it is 10 raised to power. Is it 5.6? 10 raised to power minus 10? Can you check? kV. Yes, it is 5.6 10 raised to power minus 10. Is this value very big or very small? The value is very big or very small, children? So can I do approximation safely? So approximation means I'm going to say this value approximated x. I'm going to ignore this x. So it is 0.0667, right? So I will not get any quadratic equation. I can use simple my graphing calculator. So KB is equal to, plug in here in this equation, x squared over 0.0667, which is equal to 5.6 times 10 raised to a minus 10. Can you help me here because there is no space for writing? Can you get the OH minus? Can you get the value of x? Get the value of x. That's your OH minus. You can see OH minus. Test the concentration of OH minus and get the pOH. Ready? Get the pOH, children. And then pH, because we are making a curve of pH. So get the pOH and then pH. We are doing it. How much we are getting? Okay, Vinaya, I think your answer is right. So Vinaya is giving us a pH of 5.214. Means she calculated the OH minus from this equation, the value of x, and then she converted that into pOH. So I'm taking the value given by Vinaya is, but it should be more than 7. The pH. It's a basic salt. How come you are getting less than 7? It's a basic salt. You see that you have OH minus in the solution. So pH should be, okay, Vinaya, okay. So check what is the pH then. It's a basic salt, children. Yes, yes, good. So you calculated the pOH earlier. So it means at the equivalence point, there is a sudden jump in the pH. Like this, it's going like this. And the pH at the equivalence point is basic because it is controlled by a basic salt, 786. Very good. 786. We learn from our mistakes. When you do work and you are doing errors and then correcting it, that is called as learning process. Like if I want to learn cooking, can I learn cooking without doing cooking? Just by watching the videos, can I learn? No. If I want to learn cooking, I have to go in the kitchen and do cooking and do errors. And then I learn from my errors more than what I can learn from the videos. You can learn more from your errors. And that is the reason doing quizzes on the website is extremely important. There you are going to do errors, you check your errors, and that's how you're going to learn the concept. Okay, children. So we are on the equivalence point. Now, last one, F. Ready? Shriyan, you are not answering much today. Last point, children. We are working with F point. So how much KOH? 250.0. You're listening? Listening means you're watching video, not doing cooking, Shriyan. So you want to learn cooking without doing cooking? Do the cooking. Answer here. Okay, Shriyan, listening it will not help you. Answer here. 250 and the molarity of KOH is zero point 0.1. So 250 times zero point 0.1 is 25. Yeah, Sanjana, very good. 20. Very good, Sanjana. She has made the table. Final. Now, children, final. 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 This is 5. This is 0. Who is the limiting reactant now? 20. Gracia. Who is the limiting reactant? No, Dhruv. Acid is 0. Oh, limiting reactant. Yes, acid is 0. Yes, yes, yes. You're right. Sorry. Who is going to, my question, I was thinking something else. Who is going to control the pH? Who is stronger here? Now, whatever left, who is stronger? Water is also there. KOH. But for that, I need to know the concentration of KOH. So what's the concentration of KOH? It is 5 millimoles, 5 divided by total volume. What's the total volume? 250 plus 100, 350. 350, right? Mm-hmm. How much is that? And that will be the concentration of your OH minus because KOH is a very strong base. It's going to dissociate completely 100%. So the concentration is 0.0142. But this KOH will again give you POH. It's not going to give you pH. Take the negative log of this, get the POH and then pH. pOH I'm getting 1.848. So pH is 14 minus this. If you practice using your calculator, you will see you will become very smart in plugging in values in the calculator. Like I do in one single line. I do everything, all equation in one single line. Just practice. We need practice. That's it. If I tell you, still you won't be able to do it because you need practice. No one gave me practice of using calculator. I learned on my own by using it again and again. So pH is all of a sudden there is a jump. So graph will go like this. It will go again, the space is less on the top. So can you see the pH curve, children? Now you're understood everything. The equivalence point, the half equivalence point, how to determine the pH at different intervals. So there are plenty of questions in Unit 4 also on acid-base titrations. pH curves are there. I left this topic during that time because without pH, I cannot teach you pH curves. So I left it. without equilibrium, without pH. How can we learn it? I don't know why this AP people have done this. So now you can do the quizzes of Unit 4, that acid-base titration. So that topic is covered. Okay, so that's the end of the titration questions. Now the last topic of this unit is indicators. So anyone, what is an indicator, children? What's an indicator? It indicates, is it going to indicate equivalence point or end point? Oh, come on, Dhruv. Indicator. You were there in the class when I started acid-base titrations. What's an indicator? It changes its color at the end point. It indicates the end point by changing its color. See here, Dhruv. This is the indicator which we have added one drop in this conical flask. There is no color. And after the end of the titration is always going to show you a big change in the pH, like this, big change in the pH. And this change in pH will show you a change in color of the indicator, because indicators are pH sensitive. So now I'm going to teach you why these indicators are pH sensitive. And different indicators, they have different pH range because of their different strength. So what is an indicator? Indicator is a weak acid, very weak. It's much weaker than any acid. And we are adding only 1 or 2 drops. That's why we are adding very less amount. These weak acids, now let's say this is the weak acid indicator. IN means indicator, H means acidic. This weak acid can undergo in equilibrium like this. Now, when the solution is acidic solution, then the concentration of H plus is more, is very high, very high. That will make the equilibrium shift in this direction. Le Chatelier principle, high concentration of H plus. Your indicator will be in this form, and it has a different color in this form. It has a different color. Like for example, phenolphthalein. In acid, the indicators are HIN. What's the color of the phenolphthalein in acidic condition? Colorless. This table is indicating the color. But if the solution is basic, means you added, in every titration in the last, we are adding extra base, excess of base. So if the solution is basic, the bases are going to remove this H plus. OH minus reacts with H plus to give water. The base is going to remove this H plus from the equilibrium. In which direction the equilibrium will shift? In this. And your indicator will become IN minus. And this one has a different color. Can you see that how this indicator is pH sensitive? So in acidic pH, indicators, they are like HIN, protonated. We call it as protonated. Proton is still there. Protonated, in basic condition, they are deprotonated. Protons are removed because bases are going to react with H plus. The protonated form and the deprotonated form, they have different colors. That's why indicators, they change their color when the pH changes from acidic to basic. Every indicator has a range in which it's going to change the color. Like phenolphthalein. Below 8.3, it is colorless. Above 10 is pink. So it will show you the change in color in this range. Like thymol blue. Below 1.2, it is red. Above 2.8 is yellow. Generally, these are very less used because you can see their pH range is not so good. The most important is this one, methyl red. And this one. Cresol red is also good. So they are not going to ask much questions on that, on the indicators. It's just, I'm showing you. Like, different colored cabbages you must have seen. Cabbages, red, blue, green. They are also used as indicators. Do you know, children, hydrangea plant? Have you seen hydrangea plant? It has multiple colors. They are also pH sensitive. And if the soil of the pH is more or less, accordingly, they change their color from pink to blue to purple, like this. So many things they change their color with the change in the pH. Plants also they change the color. You must have seen that they change the color with the change in the pH, they change the color with the change in the amount of the light. Okay. So this is the story about the indicators. Indicators are, can you see phenolphthalein indicator here? And methyl red. So if you go above this pH, it is yellow. If you come down, then it is red, methyl red. There is one methyl orange also. So they are the one which we are going to use with strong acids and strong bases. Why should we use them with strong acid and strong bases? The pH of the strong acid and strong base at the equivalence point is 7. And you jump straight away from low pH to high pH. So you can see that phenolphthalein can show you the change. Methyl red can show you the change. So all the indicators cannot work for every titration. You cannot say that I can use any indicator. No, you have to select the pH of the equivalence point. You have to see that, okay, the pH will be neutral. So I'll take some indicator which can show me a big change in the color during at this point, at the equivalence point. That is phenolphthalein. You go above pH 7, it's pink. And methyl red is yellow. Okay, so how to select indicator? That also is very important thing, but I think you will do it in the college level chemistry, not here. So that's the end of unit 9. I'll see you then in the next class. I'm ending the class because there is no point of starting the new unit, and we'll be starting new unit next week. See you in the next class.